Good evening. My name is Zaida Viviana Forero, and my mate is Sebastián Sandoval. We're going to explain the industrial extraction system design that we did for the exercise um, that we have to do. Now we're gonna start with the case description. The case is the following. We work in a company that produces flour in a warehouse. The warehouse has the following dimensions: length, 30 meters, wide, 20 meters, height, 3.5 meters. As workers, we realize that the operation that generates the most particulate matter is grading. Therefore, we decide to design an industrial extraction system. Given the conditions of the plant, we as engineers decide to design a cabin type hood. The conditions of the operations are the following. Equipment is a jaw mill, height 1 meter, wide 1 meter, and length 0.6 meters.
I am going to talk you about the shot solution. Therefore, considering the dimension of the mill, we decide to design the cabin type hood with the following dimension. It should be noted that our model proposes the fact that the mill is completely encapsulated by the bell with the purpose of achieve localized extraction and thus obtaining a more optimal result. Cabin dimension, height 1.85 meters, width 2 meters.
Okay, the measurements of the cabin were planned keeping in mind that the dimensions of the mill, that is the draw that we have in that slide, and the average height of a man, of a Colombian man. As the mill has a wide measurement of 1 meter, we thought of leaving a margin of 50 centimeters on each side of the mill, having a total width of 2 meters for the cabin. Regarding the height of the cabin, it was established that the average height of a man in Colombia is 1.80 meters, which is the height of the cabin was proposed as 1.85 meters, leaving a margin of 5 centimeters. This average measurement of a man was considered in the case that a worker needs to enter in the cabin in order to deposit the grains in the mill to produce the flour, or in case of having to perform any maintenance of the mill.
Continue. Well, now we are going to determine the flow rate of the bell. To do this, we will use the following equation obtained from the Industrial Ventilation Book by the American Conference of Governmental Industrial Highness Q. Where Q flow rate meters per second, BC capture speed meter per second, W width, H height.
As to capture speed, it was determined considering the dispersion conditions in which the contaminant is found. For this case, it was stipulated that the particles generated from the grading are released at a low speed, and the air conditions will be quite controlled because the mill will be encapsulated. So we found that the capture speed will be in a range between 0.5 meters per second and 1 meter per second, according to the table that we can see in this slide.
Okay, in order to determine the most relevant capture speed value, the description of the contaminant present in the lower limit and upper limit table found in the aforementioned book was taken into consideration. In this way, the particles generated by the grinding process were considered as low toxicity or nuisance contaminants. So the lower limit value was taken, which corresponds to 0.5 meters per second.
So the flow rate obtained for this cabin type hood design is the following. Where the equation is Q equal to VC per W per H. So the data that we have in this case is VC 0.5 meters per second, wide 2 meters, and height 1.485 meters. So if we perform the equation, we obtain the result of 1.85 meters per second.
Theoretical diameter. Um, Additionally, for the proposed extraction system, it's also important to stipulate the theoretical duct diameter. To do this, first it's necessary to find the cross-sectional area, for which we use the following equation. AT equal Q per VT, where ET cross-sectional area, Q flow rate, VT transport speed.
It is important to clarify that the transport speed of the contaminant was determined with the table stipulated for it in the industrial ventilation book. According to the nature of the contaminant in this case, the particles generated in the grading process to produce flow, we find that these are considered as very fine particles, similar to talcum powder. So our transportation speed is in the range between 12.5 meters per second to 15 meters per second. Thus, we took the 12.5 meters value as our transport speed. Then the cross-sectional area was calculated in the following way. Q is equal to 1.85 meters per second, as it was the result that we obtained in the last equation. VT is 12.5 meters per second. So if we did the operation, we obtain a cross-sectional area of 0.15 meters square.
Now, the theoretical duct diameter was found using the following equation, obtained by solving the equation for the circle area. D equal square root of 4 per AT per P, where the theoretical duct diameter, AT cross-sectional area. Replacing the values, the following result was obtained. D equal 0.43 meters.
Finally, we're going to determine the length of the duct if it is of the side of it is a square duct. In order to find this, the value obtained in the cross-sectional area was taken and the square was clear. In this way, we obtain the following equation. L equal to a square of AT. AT, as cross-sectional area, and L as length of the side in meters. So if we do the operation, we have the L equal to a square of 0.15 meters square. So the final result is L equal to 0.38 meters. Okay, that's all. Thank you so much for your attention.
Thank you.